and once we do that, then we have tridiagonal matrix method applied twice in order to get to the final solution. Okay. So, some more details about spatial derivatives are evaluated using central differences. To give an overall scheme that is implicit, we can see the implicitness coming from here, this delta un involving second derivative and first derivative, and that is implicit, stable and second order accurate in both time and space, and something that can be applied for viscous 2D flows. So, these schemes like these things can give rise to oscillations, and we have seen that already for the scalar transport equation involving both advection term and diffusion term. We have seen that when we use central differences we can get oscillations, but central differences guarantee a second order accuracy. So, if you want to have second order accuracy and if you do not want to have oscillations, then we need to suppress those oscillations, and those oscillations, one of the ways that was suggested early on, these are 1970s, mid 1970s and early 1980s. So, you would introduce an explicit dissipation term, fourth order method term like this, which can suppress those undue oscillations which arise because we are making use of central schemes for the space derivatives which are second order accurate. So, we have here a method which looks fairly complicated, and that is typically true of the kind of methods that we need to solve, that we need to put together when we want to solve Navier-Stokes equations. So, it is no longer a simple case of substituting the derivatives using finite difference methods. We have to take care of several factors, and the factors that we are looking at, that we are taking care in this method and also in the case of the McCormack method, are that we have not one equation, but we have 4 equations or 5 equations or 3 equations like that, coupled equations. These are coupled equations and nonlinear equations, and when we are considering viscous effects, they involve cross derivatives, they may involve normal derivatives. Okay. So, each of these things has been taken into account in coming up with an overall method which is implicit and second order accurate in its conception, and therefore, one can expect it to be stable, unconditionally stable, unlike the case of McCormack method, but explicit McCormack method. But we can see that we are not solving it in so clean a way in the process of accounting for nonlinearity and coupling. We have introduced coefficients A, P, R, which are, and S, B, Q, S. These are being evaluated at nth time step, okay, at the previous time step values. So, these are not the latest values, it is not fully implicit. Part of it is explicit and part of it is implicit. And what this means is that if you take very large time steps, because your scheme is stable for any value of delta t, then in the process of taking long time step, you are freezing the contribution of the nonlinearity and coupling to the previous time step value, and that can give rise to problems. So, when in a case where so essentially what you are saying is, while you are solving the u equation, you are expecting the contribution to these things coming from the VA and W and those kind of things are frozen at the previous values, previous time step values. That is possible only for small values of delta t, not very large values of delta t. So, when you take too large a time step, then you have problems that can arise because of this lagging of the coupling and nonlinearity terms, and so that can mean, that can limit your delta t values that you can take. Okay. So, in using, when we are looking at compressible flows, we have examined two popular well put together methods, and what we can see from this is that these methods require some special putting together in order to make them solve Navier-Stokes equations and the governing equations in different forms. And we have to take special considerations to bring in, to take account of nonlinearity, coupling, and the cross derivatives and normal derivatives. And we have seen that these schemes are limited in their time step, and in the case of the McCormack scheme, the delta t, as we have seen, is a function of the speed of sound, and the speed of sound becomes very large for nearly incompressible flows and is infinity for totally incompressible flows where density does not change. And when A becomes infinity, the delta t CFL becomes infinitesimal, and so that means that you cannot progress in time. You can progress with in time with infinitesimal time steps, and that is realistically not possible. If you go for the implicit methods, you can go for larger time steps, but again you do not want to have such a large time step that the CFL condition is okay. So, the delta t is too large, because as you are changing u, v and w are also changing, and you are not taking account of that. So, there are densities also changing and enthalpies are changing. So, all those things are simultaneously changing, and so for implicit methods also one usually recommends a delta t which is not more than 10 times the delta t that you would use with the corresponding explicit method. So, that means that the methods that we have looked at for compressible flows cannot be straight away used for incompressible flows, and so this gives us a problem. Have been successful in extending the compressible flow methods, like some of which we have seen, to incompressible flows, but there has also been a separate movement towards developing special methods for incompressible flows. And as part of this course, in the next half of this module 4, we will be looking at methods that have been specially derived for incompressible flows. And here we have we lose the advantage that is present in compressible flows of a natural linkage between the continuity equation and the momentum equation, because in the continuity equation you have dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v equal to 0. You have that equation, and you can use that equation to get density, and once you have density and the internal energy from the energy equation, then you can use an equation of state to get pressure and temperature. So, that kind of linkage between the continuity and the momentum equations is not present in the case of incompressible flows, because there is no density term that is coming in the continuity equation. So, continuity equation is also in two dimensional cases, it is just dou u by dou x plus dou v by dou y equal to 0. So, there is no pressure, there is no density, and this creates a special problem because of this loss of linkage. And you can say that there are 3 or 4 different approaches for dealing with this, and these are the ones that we are going to discuss in the second part of this module. So, we will just look at what these methods are. So, the first one is about artificial compressibility. Okay. So, if compressibility does not exist, if there is no relation between density and pressure, if there was a relation, then we could have evaluated the density from the continuity equation and gotten the pressure from the equation of state, which would be linking pressure and density through the compressibility. So, if there is no compressibility, then we could artificially introduce a compressibility and then create a linkage between the continuity equation and the momentum equations. So, something like this can be created and the resulting method would work, but it is a problem of the equations. The equations have been tampered with by introducing an artificial compressibility. So, what we will see is that this method will work and is correct, it is solving the correct equations in the limiting case of steady flows. Okay. So, that is one approach that has been taken. If you want to do steady incompressible flow calculations, then you can introduce an artificial linkage between the continuity and the momentum equation by introducing a fictitious equation of state and fictitious compressibility, and then you can get a solution for steady state, and under steady conditions the equations are correct, the equations that you are solving are correct, but the transient part is not really truly reflective of that. So, there is a limited applicability, but that is one approach by which you can solve for steady incompressible flows, and it is an extension of the methods that you have already developed for compressible flows. But there is a different way of looking at it, different way of solving it. Since pressure is the nuisance variable, in the sense you have pressure is there in the x momentum equation, which will give us the u velocity, it is there in the y momentum equation, which will give us the v velocity, but it is not there in the continuity equation, which should give us density and from which the pressure in the case of compressible flows, and in the case of incompressible flows we do not have that luxury and pressure does not appear in that. So, is it possible to eliminate pressure completely from these three equations? We can do that by introducing two new variables, stream function vorticity, and the three equations, that is the continuity, the x momentum and the y momentum equations, can be rephrased into two coupled equations involving stream function vorticity, in which there is no pressure and the variables are stream function vorticity, and you can solve these two equations for these two variables and deduce from that the velocity, and after having gotten the velocity you could then separately solve for pressure. So, this is a method which can get rid of that vexing question of pressure by completely eliminating pressure from the Navier-Stokes equations. But unfortunately this method is applicable only for 2D flows. Only in 2D flows you have the concept of stream function. If you extend it to 3D, then you get into quite large number of coupled equations, even more than what you have dealt with, and that makes it very complicated. So, if you are looking at either steady or unsteady 2D flows only, then in whether it is Cartesian coordinate system or cylindrical or polar, you could come up with the stream function vorticity method to solve the corresponding equations without worrying about the pressure. And so, this is a different approach, different from what we have seen in the first case, which is the artificial compressibility. There is another possibility, that is, since pressure evaluation is something that is difficult for us, if you can rewrite, if you can derive an equation for pressure from the continuity and momentum equations, and if we then, what it would mean is that if you know the velocity you can calculate pressure, and if you know pressure you can calculate velocities. So, you would first solve for velocities, and then from that you would get pressure, and then you put the pressure back and then get velocities. So, you can have either an explicit pressure equation method or an implicit pressure equation method. You can alternately solve the momentum equations with assumed pressure and then solve for velocities, and then use the velocities to get an improved value of pressure, and then you can put it back and then forward. So, you you are solving a pressure equation, you are solving a reformulated set of momentum Navier-Stokes equations, still using the same primitive variables u, v and w and p, and that is known as the pressure equation, the variants like Mach scheme and all that, and so that is one possibility which can be used for transient 3D flows, unlike artificial compressibility method which can be used only for steady 3D flows, unlike stream function vorticity method which can be used for transient flows but only 2D flows. Pressure equation method can be used for both. Pressure correction is in a way it is a variant of the pressure equation method, where you are trying to say that I have a guessed pressure field and it is obviously not satisfying the continuity equation. So, I would like to correct the pressure by a small amount and then in such a way that the velocity also gets corrected and the corrected velocity will satisfy the continuity equation. So, that idea is formulated in the form of an algorithm where you will be solving not for pressure directly, but for pressure correction. So, these are the 4 methods that we will examine for specifically for incompressible flows, and of these the pressure correction method is the most popular, especially for internal flows, and it has been used in a reverse way. A method which has been developed for incompressible flows has been extended to compressible flows, but it is something that we do not discuss as part of this. So, you have truly compressible flows methods that can be extended in theory to incompressible flows, and methods that have come from incompressible flows extended to compressible flows. So, in a way there is some sort of merging of the streams, but people still use hardcore compressible flow, people use specialized methods which have been developed for compressible flows, and hardcore incompressible flows like automobile engineers or maybe chemical engineers and these kind of people who consider not just the flow but lots of other things like combustion, chemical reactions and all that kind. In such a case the pressure correction method is found to be more robust and it enables you to model allied phenomena in an elaborate way. So, that is where it is in that is probably the reason why pressure correction methods have become very popular and often used for incompressible flows and slightly compressible flows in many process industries. So, in the second week of this module 4 we will be looking at the basic ideas in these 4 methods. I would like to end this module, this part of the module by emphasizing that we are not looking as part of this course developing methods which are developing codes which can do all this kind of calculations. We are just trying to understand the principles and understand the concepts which have been developed to deal with the real Navier-Stokes equations, and we can see a lot of difference between the way that we are solving the Navier-Stokes equations and the simple concepts of stability, consistency and convergence, those kind of concepts that we introduced in module 3. So, we can still see some remnants, some traces of those in the methods that we actually use for Navier-Stokes equations, but the expediency of practicality of having to deal with viscosity, turbulence and all those kind of things, which involves more and more coupling and more nonlinearity and all that. So, we can no longer afford that luxury of consistency and total guaranteed stability. We have to compromise on that and come up with methods which can give rise to a solution which can give us a solution, and it is always therefore necessary for us to validate our CFD simulations of real flows. That is something that we would like to keep in mind. So, thank you.